What allowed Earth to survive when countless other worlds could not? Most other planets failed from the very moment of their formation, destroyed by extreme conditions and relentless cosmic storms. From space, Earth appears as a mysterious blue world. Yet beneath that beauty lies an extraordinarily fragile reality. Earth began forming about 4.5 billion years ago, emerging from clouds of gas and cosmic dust within a region of the Milky Way. From a catastrophic collision with the planet Theia to the presence of a molten iron core that generates a protective magnetic shield, each stage shaped its fate. Positioned within the habitable zone, where temperatures are just right for liquid water to exist. According to scientists, roughly 70% of the planet's surface is covered by water. These factors, along with many other conditions, created a truly unique planet, one where life could arise and continue to evolve over millions of years. We are beginning a journey to explore one of the greatest survivors of all. The story of the birth of planet Earth. Around 4.6 billion years ago, Earth was nothing more than a vast molecular cloud, cold, dark, and diffuse, drifting through interstellar space. Within it was a mixture of hydrogen, helium, and heavier elements such as carbon, silicon, iron, and oxygen, the legacy of supernova explosions from generations of stars that had lived and died before. For a long time, this cloud existed in a fragile state between balance and collapse. Thermal pressure pushed back against gravity. A small disturbance, perhaps a shock wave from a nearby stellar explosion, was enough to break that balance. When the density of matter crossed the gene's instability threshold, gravity began to dominate, and the cloud contracted, collapsing in on itself. At the center of this collapsing mass, matter was compressed until nuclear fusion reactions ignited, and the sun was born. But its formation was not an ending. It was the beginning of a far harsher environment. Not all of the remaining material fell into the central star, but instead spread outward into a flat, rapidly rotating protoplanetary disk. This disk was a chaotic region where swirling gas streams, colliding rock fragments, and constantly distorted orbits defined its nature. Within this protoplanetary disk, evolution followed, not biological rules, but the brutal logic of physics. Micron-sized dust grains collided and stuck together through electrostatic forces. They grew into larger aggregates, then grains, then pebbles. And once they reached sufficient size, their own gravity began to matter. From there, the process of accretion accelerated, forming kilometer-scale rocky bodies known as planetesimals. These continued to pull in surrounding material, colliding with one another in impacts of enormous energy. From planetesimals, planetary embryos emerged, but Earth was not special at this stage. It was just one embryo among hundreds coexisting in the inner region of the young solar system. Each embryo was a candidate, and most failed. Some were swallowed by larger embryos. Others were flung out of the nascent planetary system by gravitational interactions. Still others were crushed in collisions that released enough energy to melt their entire surfaces. During this phase, Earth survived only provisionally. With each impact being both a threat of destruction and an opportunity for growth. Every incoming fragment could make Earth larger or erase it entirely. The surface was not solid ground, but a magma ocean, where temperatures were high enough for metals and silicates to separate into layers. To understand why Earth was granted this fragile window of survival, we must look toward Jupiter, the giant that silently shaped the fate of the entire solar system. Unlike Earth or Mars, modern models of planet formation, combining observations of protoplanetary disks around young stars, show that Jupiter appeared extremely early, just about 1 to 3 million years after the Sun was born. While most of the material in the protoplanetary disk still existed as hydrogen and helium gas, Jupiter had already formed a massive solid core, with an estimated mass of about 10 to 20 times that of Earth. Once this core reached a critical size, runaway gas accretion began. Jupiter pulled in the surrounding hydrogen and helium at an ever-increasing rate, rapidly becoming a gas giant with a final mass more than 300 times that of Earth. Jupiter's gravity does more than hold its moons in orbit. It dominates the entire dynamical structure of the planetary disk. It distorts orbits, stirs material, and alters the evolutionary paths of every other world. When we observe planetary systems beyond our own, a troubling pattern emerges. Wherever gas giants form early and migrate inward, super-Earths often appear, rocky planets several times more massive than Earth, orbiting close to their host stars, hot, dense, and utterly hostile to life as we know it. According to the Grand TAC model, developed from dynamical simulations and the current mass distribution of the terrestrial planets, Jupiter did not remain at its original position after forming. Interactions between Jupiter and the surrounding gas disk generated torques that caused it to migrate inward, possibly approaching about 1.5 astronomical units. A region not far from the present-day orbit of Mars. During this journey, Jupiter acted like a colossal gravitational mixer, disrupting and pushing material out of the inner solar system. A gas giant invading the inner region is usually a death sentence for rocky planets. But the universe does not follow simple scripts. When Saturn formed and reached sufficient mass, it began to interact strongly with Jupiter. The two planets entered an orbital resonance, a dynamically stable yet highly consequential state. The name Grand TAC, borrowed from nautical terminology, reflects a maneuver that reshaped the entire solar system. The inner region was depleted of material, preventing rocky planetary embryos from growing too large. The outer region, by contrast, remained rich in gas and ice, allowing giant planets to continue developing. The result was a sharply divided planetary system, small rocky planets inside, massive gas giants outside. It was precisely this lack of material that prevented the formation of super-Earths in the inner region, an outcome that is rare when compared with statistics from exoplanetary systems. Earth, therefore, is the product of a system profoundly altered by planetary dynamics. Jupiter is often described as a gravitational shield protecting Earth from asteroids. But in this early phase, it was no guardian. It disrupted planet formation, eliminated many potential candidates, and left behind only a few worlds small enough and stable enough to continue existing. yet by disturbing the orbits of the surviving embryos, Jupiter indirectly increased the likelihood of late collisions. The final impacts that shaped Earth's physical nature. Among them was one collision that did not merely alter the surface, but redefined the planet's climate future, axial tilt, and rhythmic stability for billions of years to come. It was the moment when Earth ceased to be merely a surviving planet and began to become a stable system. It was not the cooling of the surface, nor the appearance of water or an atmosphere, but a planetary collision on a catastrophic scale. An impact powerful enough to restructure Earth from its core to its orbit, yet precise enough not to erase the planet entirely. Out of that event, the Moon was born. Around 4.51 to 4.47 billion years ago, Earth entered the Hadean Eon, a period when the planet bore no resemblance to the world we recognize today. The surface was not solid ground, but a global magma ocean, constantly boiling, solidifying, and melting again. Heat at that time came from three main sources: the residual energy of planetary formation, the radioactive decay of elements such as uranium and thorium, and a still high frequency of impacts. It was within this environment that another planet approached, known to science as Theia. Dynamical and chemical models indicate that Theia was roughly the size of Mars, with a mass of about 0.1 times that of Earth. It was not a wandering minor body, but a true planetary embryo, existing alongside Earth during the final stages of terrestrial planet formation. Theia did not strike Earth head-on. Instead, simulations point to an oblique collision with a relatively shallow angle and an impact velocity of about 911 kilometers per second. The key lies in how material separated after the impact, with most of Theia's dense iron core sinking and merging with Earth's core. Increasing the size and density of Earth's metallic center. Meanwhile, lighter, silicate-rich material from the mantles of both Earth and Theia was ejected into space. Forming a disk of molten debris orbiting Earth. This was not a random dispersal, but the inevitable outcome of impact dynamics and density differences, within planetary materials. From this debris disk, over just a few thousand to a few tens of thousands of years, material began to reaccumulate under gravity. Models show that the Moon formed relatively quickly on geological timescales. Lunar rock samples returned by the Apollo missions reveal oxygen isotope ratios that are nearly identical to those of Earth. Within measurement uncertainty, in the solar system, each body typically has distinct isotopic ratios, reflecting where and how it formed. This near-perfect similarity indicates that Earth and the Moon share the same source reservoir of material. Something alternative hypotheses struggle to explain convincingly. This impact did more than create the Moon. It reshaped Earth's dynamics. After the collision, Earth rotated far faster than it does today. Estimates suggest that a day may have lasted only 4 to 6 hours. Over time, tidal interactions between Earth and the Moon slowed Earth's rotation while pushing the Moon gradually outward. At a present rate of about 3.8 centimeters per year. This evolution was not merely mechanical. It directly influenced future climate and biological rhythms. Most crucial of all was the stabilization of Earth's axial tilt. Earth's axis is tilted by about 23.5 degrees, giving rise to the seasons. Long-term simulations show that without the Moon, Earth's axial tilt could vary chaotically under the gravitational influence of other planets, swinging by tens of degrees over relatively short timescales. The Moon, with a mass equal to 1/81st of Earth's, acts as a gravitational stabilizer, keeping Earth's axial tilt within a narrow range for billions of years. The very event powerful enough to erase all original surface structures became the prerequisite for long-term stability. Life on Earth is not the result of a gentle process, but of a cosmic accident balanced perfectly by probability. After the collisions that shaped Earth's geometry and dynamics, the planet entered a more subtle yet equally brutal challenge. Holding on to water and an atmosphere. Earth's water did not come from a single source. Analyses of the deuterium to hydrogen ratio in ocean water show a striking similarity to carbon-rich meteorites suggesting that part of Earth's water was delivered from the outer solar system during the late heavy bombardment. These meteorites contained water in the form of ice and hydrated minerals. And when they fell onto the young Earth, they added to its surface water inventory. Yet geochemical data also point to another source, quieter and more persistent: endogenous water. Within Earth's interior, water can be locked in the form of hydroxyl groups within silicate minerals in the mantle. During the first few 100 million years, the sun emitted ultraviolet and X-ray radiation 2 to 5 times stronger than today. Along with a dense solar wind of charged particles. These processes can strip a planet's atmosphere through erosion and atmospheric escape, especially removing light gases such as hydrogen. With only about 10% of Earth's mass, Mars cooled rapidly, causing its metallic core to solidify early and its global magnetic field to disappear within the first few 100 million years. Without a magnetosphere, the solar wind directly eroded the Martian atmosphere. Orbital data show that Mars once had liquid water, rivers, and lakes. But as the atmosphere thinned and pressure dropped, surface water became unstable and was lost to space. Mars did not fail because it lacked water at the beginning, but because it could not keep it. Earth's survival hinged first on sufficient mass to retain an atmosphere over long periods of time. Second was the early formation of a magnetic field. Paleomagnetic studies of ancient zircon minerals suggest that Earth may have possessed an active magnetic field as early as about 4.2 billion years ago. This field generated a magnetosphere that deflected much of the solar wind and dramatically reduced atmospheric loss, especially of hydrogen, the key to retaining water. At a deeper level, the coupling between oceans and atmosphere created large thermal inertia, reducing the amplitude of climate fluctuations. Water absorbs and redistributes energy efficiently, while the atmosphere transports heat from the equator toward higher latitudes. A planet with stable water and atmosphere does more than survive. It remembers, accumulating states over time rather than being wiped clean after each random catastrophe. When Earth retained its water and atmosphere, it preserved not just material, but potential, the potential for chemistry to grow complex. For energy to be distributed slowly through oceans and air. For reactions to persist long enough for new structures to emerge. A planet that keeps its water is a planet with a long history, where the past can layer upon itself instead of being erased. Yet water and atmosphere only set the stage. Once that stage was ready and endured long enough, a deeper phase transition occurred. Matter began to store information. From deep oceans and chemical energy sources, early life emerged. And Earth entered a phase in which it no longer operated solely under physics, but began to remember itself. The next chapter is that moment, the emergence of life, and the first time this planet gained memory. When Earth managed to retain its water and atmosphere for long enough, an invisible threshold was crossed. There was no explosion, no brilliant moment visible from space, yet from that point on, Earth was no longer just a purely physical chemical system. It entered a new state, one in which matter did not merely react and disappear, but preserved the consequences of its own processes over time. That was the moment life emerged. And with it, the planet began to remember. The oldest evidence suggests that life appeared very early in Earth's history. Carbon isotope analyses in sedimentary rocks from Greenland and Western Australia, dated to about 3.8 to 3.7 billion years ago, show a clear preference for carbon-12 over carbon-13, a distinctive signature of biological processes. Early life did not arise on the harsh surface, where ultraviolet radiation was still intense and small impacts continued to occur. Instead, a growing body of evidence and biological models points to the deep ocean as life's cradle, particularly around hydrothermal vents. There, cold seawater met hot rock from the mantle, creating extreme thermal and chemical gradients. These energy gradients, not sunlight, provided a stable energy source for prebiotic reactions. Hydrothermal vents were rich in hydrogen, methane, sulfides, and metals such as iron and nickel. These components enabled simple redox reactions, generating a continuous supply of chemical energy. In such environments, organic molecules could accumulate, combine, and replicate in rudimentary ways. Early life did not require complex DNA or fully formed cells. It needed only the ability to maintain structure in the face of chaos. Earth's atmosphere at that time was completely different from today's. There was no free oxygen. The sky was filled with carbon dioxide, nitrogen, methane, water vapor, and sulfur compounds. In this environment, oxygen was a highly reactive substance, destructive to biological structures. As a result, the earliest life forms were anaerobic microorganisms, drawing energy from chemical reactions with their surroundings. They did not transform the planet or engineer the atmosphere. They simply existed in the narrow gaps permitted by physics. Over hundreds of millions of years, simple biological systems experimented with countless ways of exchanging energy. One of the most revolutionary innovations was photosynthesis. At first, photosynthesis did not produce oxygen, but used compounds such as sulfides or iron as electron donors. Then, around 2.7 billion years ago, a lineage of microorganisms, cyanobacteria, developed the ability to use water as an electron source. The byproduct of this reaction was oxygen. Much of the existing biosphere was wiped out. But this was also the turning point that opened a new era. The organisms that survived were those that learned to tolerate oxygen and eventually to exploit it through aerobic respiration, a process capable of producing far more energy than anaerobic pathways. The accumulation of oxygen in the atmosphere led to the formation of the ozone layer, reducing ultraviolet radiation at the surface and opening the way for life to move into shallower waters and eventually onto land. The oceans absorbed carbon dioxide, regulating global temperature. The carbon cycle, combined with plate tectonics, acted as a negative feedback system, helping Earth avoid extremes of heat or cold over billions of years. Life was no longer merely adapting to the planet. It had begun to participate in running the planet. From anonymous microorganisms in the dark ocean depths, Earth gradually became a world where geology, climate, and biology were tightly intertwined. This did not make the planet permanently safe. On the contrary, it introduced new crises: mass extinctions, cycles of collapse, and reorganization. But it created continuity, the capacity for the planet to evolve. Rather than being reset to zero after every catastrophe. The birth of Earth was not a brief, random event, but the result of a long and persistent process of construction spanning hundreds of millions of years, emerging from the chaotic disk of materials surrounding the young sun. The gradual accumulation from microscopic dust grains to catastrophic collisions between planetesimals forged a complex geological body. At the very heart of this chaos, structural differentiation unfolded with remarkable precision. A molten metallic core formed, generating an invisible yet resilient magnetic shield that protected the planet from the destructive force of cosmic radiation and preserved its early atmosphere. As relentless meteor showers delivered water-bearing minerals and essential organic compounds, Earth's surface began a historic cooling process, transforming from a blazing magma ocean into a solid rocky crust. The emergence of liquid water and the stabilization of geochemical cycles marked a decisive turning point, converting what had once been a dead world into an environment capable of sustaining life. The story of Earth's formation is not only an explanation of our material origins, but also a testament to the extraordinary alignment of physical laws. Within a vast and hostile universe, Earth stands as a rare oasis, a legacy shaped by time itself, reminding us of the fragility and singular value of this blue planet within the infinite cosmic landscape. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.